Alright, welcome back. We're going to finish part 2 of the video dealing with applications of law of sines and law of cosines. So another example here. A boat is sailing due east parallel to the shoreline at a speed of 20 miles per hour. And at a given time, the bearing to a lighthouse is south 68 degrees east, and 30 minutes later, the bearing is south 52 degrees east. Find the distance from the boat to the lighthouse at a boat position 2. So we have our shoreline. A boat is traveling parallel to it, so we know it's traveling this direction. So we're going to say boat position 1, and then we'll say boat position 2, knowing the fact that it's moved parallel to the shoreline. So currently boat position 1 in relationship to the lighthouse, so we'll put LH down here for lighthouse, is traveling at a speed of 20 miles per hour at a given time. The bearing of the lighthouse is south 68 degrees. So we're going to look south first. So my original crosshairs, oops, I should probably change color here for you. Original crosshairs, it's going to be south 68 degrees east. So when I connect the boat to the lighthouse to 68, it's going to go on the outside because we're originally, again, starting south, looking to the east. We don't know that distance yet. We don't know how far boat 1 is to the lighthouse. We just know that it's gone at least south 68 degrees east. And then 30 minutes later, the bearing for the boat 2 is south 52 degrees east. So this one, we're going to look directly south. And then to get down to this spot, obviously the picture not drawn to scale here, we're going to say is 52 degrees is going to be right here in that bearing, because we're looking south and then we're looking to the east. So on the inside we have a 52 degree angle, which means right here, to finish that off, because we already gone from west down to south, is 90 degrees. And then looking at over here, we know that the inside one on this one is going to be 22 degrees to finish off that full turn from the south straight to east. So these have to equal 90. This has to equal 90 turn plus the 52 degrees that takes you a little bit further. So we've taken care of the bearing here. We've taken care of the bearing here. And right now we have 22. We have 142 for our total angle here. And then knowing that a triangle has to add up to 180, we have a total of 164, which leaves us 16 degrees down below. So if I were to kind of just redraw this triangle just to kind of give us a little bit better mark here, we know that the inside here is 22 degrees. We know that this down here is 16 degrees. And that full revolution, or that full turn from boat 1 to boat 2 to lighthouse, is 142 degrees. So we have 3 angles, which technically isn't enough to use law of sines or law of cosines. But there's something we haven't used yet. We haven't talked about the speed at which it's traveling. We're traveling at 20 miles per hour, and we've gone 30 minutes so far from boat 1 to boat 2 position. So we have to take 30 minutes of an hour, or 60 minutes, which is a half. So therefore we've traveled 10 miles in this 30 minutes that has passed. So now we have the 10 miles there. So it says find the distance from the boat to the lighthouse at boat position 2. So when we're actually solving this, now we're putting in our unknown variable. I'm looking for this value first. So if x is here, now using the process that we've learned the last couple days and reviewed on, is we're going to go with sine of 16 degrees over 10. And it was important that we found this 16 degrees and we found this 10 down here because, or this distance 10, because now we have an angle and a side that match, which allows us to to use the law of sines. So my setup is sine of 16 over 10 is equal to sine of 22 over x. And then we cross multiply these two products, so we take 10 times the sine of 22. So again, we take 10 times the sine of 22, and when you do that in your calculator, you get 3.746. And then we divide that by sine of 16, and you're going to get a distance of 13.591 miles. So boat 2 to the lighthouse is equivalent to 13.6 miles. Now a little follow-up on this, and I don't ask this on this question, but I could in the future. And that kind of question would be, at what angle is the lighthouse to get to boat 2? So if boat 2 we know that it's traveled 13.6 miles, and I want to know what angle from the lighthouse to get to boat 1 based on north. So if I'm looking for lighthouse to boat 1, I'm going to draw my crosshairs in here. We know that this is 90. So we kind of have this angle down here coming in and leaving. We know that this is 16 degrees. And then we don't know the combination of these quite yet. We just know it's a 90-degree turn. But the key thing is that because these lines are parallel, if this is 22 degrees, then this bottom angle has to be 22 degrees as well because of alternating interior angles. So 22 degrees, 22 degrees. So now that allows me to say, if I want to know to get to boat 1, which is up here, the angle measure at which it would turn would be north, this whole value, so north, and we know this is going to be 90 minus the 22. So 90 minus the 22 is north 68 degrees to the west. This would be the coordinates or the bearing you would give from the lighthouse to get to boat 1. Now I know that 16 degrees doesn't seem like it's important, but that 16 degrees is made up inside of that 68-degree angle that was created. But this was our main question for right now. We'll get a lot deeper into these when we get into vectors. All right, last example for today. A pole is tilted towards the sun at an 8-degree angle from vertical, and it casts a 22-foot shadow. The angle of elevation from the end of the shadow to the top of the pole is 43 degrees. How tall is the pole? So we know that here's our sun looking down out here, and this pole that's on the ground is tilted at an angle of 8 degrees from vertical. So straight vertical would be this direction, and since it's tilted towards the sun, this 8 degrees is actually going to go on the inside. Since the initial from vertical is up and down, so now it's 8 degrees away from the vertical. So the 8 is going to be on the inside, which makes this one 90. And we know that it casts a 22-foot shadow. So since the sun is coming down hitting the pole here, the shadow is going to be created at this value. So we go 22 foot. So the angle of elevation. So you took care of the 8-degree angle from vertical, and you took care of the 20-foot shadow. Now we need to focus on the angle of elevation from the end of the shadow to the top of the pole. So end of the shadow to the top of the pole. Now I tell you that the angle of elevation, so you're looking up, we want to think of elevation as looking up. So I'm starting here looking up at the sun, has an elevation of 43 degrees. So the question is, how tall is the pole? So looking at the scenario that we have, we look at the given information, we realize that we have an angle, side angle relationship. So we're given A SA. So again, I like to just redraw the triangles just to make sure that I have every information. I know this is 98 degrees with the fact that these two add up. I know I don't know this distance. I know that this is 22 feet. And that angle over here is then going to be 43 degrees. So I really know that top angle. So if we take 98 plus 43 and subtract that from 180, we get 39 degrees. So 39 degrees is this top angle. So we can go, A, B, C, or you can label any letters you want. But now since I have an angle and a side length that match, it's easier for us to find out how tall the pole is, because now I can go sine of 39 over 22 is equal to sine of 43 over x. And when you solve for x, your exact value should be 22 sine of 43 all divided by sine of 39. Since this is a story problem, I want you guys to get the exact value. So we're going to take 22 sine of 43 divided by sine of 39, and you get x, which is equal to 23.84 feet. That's how tall the pole would then be, with an angle of elevation of 43 degrees and being tilted at an 8-degree angle from vertical. Obviously, if we increase the angle, that distance is going to decrease a little bit, because that will affect the angle at the far end. So I'm hoping by now things are starting to click with applications, but since we are this deep in the applications, and especially with 7.1 or 7.4 day one lesson, I already started off with a lot of applications just to kind of get you guys thinking about more of it. I feel like the application should give you more context to it. So this should feel like a review. The goal would be next class that you have worksheet 7.5 applications. 1 through 4, I want you guys to pick 3 of them. That's a little bit of the review from last class in terms of, do you have 1 triangle or 2 triangles? And then 5 through 14 are the story problems. I know I don't give you a lot of room to do them. I encourage you to do them on a separate sheet of paper. I'd like you to pick any 6 of those. But please, don't just try and pick the 6 easiest ones. Really make sure that you are hitting all levels. So, kind of pick through, look at which ones are going to challenge you. The hardest part is just getting the pictures. And then you have to do 15 and 16. So your requirements are 1 through 4, pick 3. 5 through 14, pick 6. And then questions 15 and 16, which will be due next class. And I should be, if everything goes according to plan, I will be there next class to kind of start getting things reviewed and get ready for our test, which is coming up next week. Hope all is well, and I'll see you guys soon. Thanks.